Okay, so we continue on our discussion of laminar flow. Um,
That's that dude's name.
so you are being recorded right now while you're talking. Okay, sorry about that. That was my mom talking. Um, Q is equal to integral subtube VdA volume. I hope you caught me there. Obviously, V is velocity, not volume. I don't know why I said that. This integral here is equal to integral of r naught squared minus r squared over 4 mu multiplied by the pressure gradient, p sub 1 minus p sub 2 delta x multiplied by 2 pi r dr, which is the circumference. This, in turn, is equal to the pressure gradient multiplied by pi over 2 mu multiplied by the difference of r naught squared multiplied by r squared over 2 minus r to the fourth over 4, which in turn is equal to pressure gradient multiplied by pi over mu multiplied by r naught to the fourth over 8, which finally equals pressure gradient multiplied by pi over mu multiplied by the diameter to the fourth over 128. That equation is sometimes known as the Poiseuille-Hagen equation, named after the two men who helped derive it. From that equation, it can also be shown that the average velocity is equal to volumetric flow rate over pi r squared is equal to Vmax sub 2. So essentially stating V average is equal to Q over pi r squared equaling V sub max over 2. And the average kinetic energy is equal to the integral V squared over 2 multiplied by dq. This is divided by integral dq. And q, this dq, integral of dq is q. So this is going to become q is equal to volume times the area, or times the circumference rather. Velocity times the circumference. So it's integral of v multiplied by 2 pi r, which is the same as q. This is supposed to have a dr2, but you probably won't be able to read it. Whoops. Whoops. Okay. So we have here, this is equaling integral of v squared over 2 multiplied by v multiplied by 2 pi r dr over the integral of v multiplied by 2 pi r dr. Do you see how I'm getting this here? This is going to be q. Integral of dq is q. Q is equal to integral of v multiplied by 2 pi r dr. If we took the integral of this, the integral of v is v squared over 2. The integral of 2 pi r. 2 pi r is going to be pi r squared. And I'm sure you notice the difference right away. That's going to be equal to q, the volumetric flow rate. So it makes sense that this becomes integral of v multiplied by 2 pi r dr. Up here, v term appears. Again, similar to what happened down here, q becomes 2 pi r v times 2 pi r dr. So this and this are similar. The only difference is that v squared over 2 is in the numerator as opposed to where it is not present in the denominator. So we resume. And that integral, that previous equation that I just showed you, is equal to the average velocity squared. So now this fits into Bernoulli's equation. We find the friction heat loss per pound mass, which is denoted by that fancy F. Is equal to the negative change in pressure over the density whoops is equal to the volumetric flow rate multiplied by delta x multiplied by the viscosity divided by the density multiplied by 128. That's not a coincidence, that showed up in the last equation. Divided by pi d naught to the 4th power. Now this friction heat loss term is also equal to negative acceleration multiplied by the change in height. Which is the same as Well, guess what it's the same as? Guess what this term is equal to? Well, if this is equal to F, the friction, the fancy F, friction heat loss per pound mass, and this is equal to F, well, this is equal to F, so this, by the commutative property, this is going to be equal to that, so it's equal to Q delta X, viscosity over density multiplied by 128 over pi diameter to the fourth. If you can't memorize these formulas, at least have these on a sheet of paper. At least for our test, our professor allows us to have a little bit of a cheat sheet, a couple pages, write all these formulas down. This is definitely one to write down. Thus, for either horizontal or vertical laminar flow, we find that this fancy F term is equal to Q delta X mu over rho multiplied by 128 pi over d naught to the fourth. So this is really important. And this is for laminar flow only, not turbulent. If you use this for turbulent flow, you will assuredly get the wrong answer. Laminar only. There are examples you can do in your book that are done in the book for you. I find that if I do the examples out of the book, it's sort of tedious and it's not really of a use. I'll explain concepts. I will do unsolved problems at the end of chapters, but doing examples that are already solved out for you, they've already done it for you, so why would I solve them out for you? So I say look at the examples in your book, and try to get at least a foundation of what they are talking about, of what they are explaining. I guarantee you that your book has problems that relate to laminar flow, that ask you to find, for example, the pressure, using Bernoulli's equation, finding gauge pressure, finding, let's say, the fluid density, or finding the Reynolds number, or what have you. So look over these, and that will be important. This concludes our discussion of laminar flow. In the next video, we will discuss turbulent flow. See you then.